BigSmall. This may be one of the most powerful in the sense that it brings together so many different things that get students confused. From the reversing that comes in with division, which is related to BigSmall, and then all the number conversions, doing stuff on one side of the equation to make this or that thing happen. What's the rule that I follow? What's the action that I take? BigSmall, it's used a lot. And I'm sure I'm not going to be able to give an example of everything. Once you begin seeing it, you're going to see it more and more in whatever textbook, whatever curriculum you're using. Okay, let's get started on this. BigSmall. Make part of the object bigger and the other part smaller by the same size, and use the current operation. So, complementary to balance, we're going to have two opposite effects on one object or one side. This never crosses the equal sign. Balance, remember, was one effect, two sides. This is two effects, one side. So here's some examples now. First, I guess a little practical illustration. BigSmall is like squeezing a water balloon. One part gets bigger while the other part gets smaller, but the total amount of water stays the same. The value of the problem stays the same. You're not actually changing it. For example, right here, when we have 9 minus 6, if I subtract 1 from the 9 but add 1 to the 6, I'm still the same. 9 minus 6 is the same as 8 minus 5, which is 3. Notice 9 minus 6 is 3, 8 minus 5 is 3, 3 is 3. It stayed the same. It's not an equation. I just have equals. Sometimes I use the becomes arrow, but a lot of people aren't used to that, so most of the time I use equal. But 9 minus 6 becomes 8 minus 5, and 8 minus 5 becomes or is equal to 3. You get the before and after. So value does not change. Our change is counterchanged, and that keeps it the same. So I think you can then see the rest of what we've got going on down here. 2 minus 1, 7 plus 1. Notice the two opposite effects on one object, and this object is an expression. Back with zoom levels. See the intro video, see the sort action, talks about zoom levels. So 2 subtracts 1 to 1, 7 adds 1 to 8. Both before and after equal 9. I've never changed the value. And I used the current operation. 2 and 7 are two separate terms connected by combining. So I'm going to use combining. I added and subtracted. Up here, I was combining the 9 and the 6. I combined 1 to both of them. Down below, now I am multiplying. So I'm going to use multiplying and or dividing to change my numbers. So 4 times 2, I make it twice as big. I make the 6 twice as small. 8, 4 times 2 is 8, 6 divided by 2 is 3. Notice I have 24 all the way across. The value never changed. The numbers did, but the value, the total value, didn't. Now down here, we've got division. Something else to think about here, and division reverses things. You think, well, wait a minute. I have two opposite effects. Notice I did not say two opposite operations. I said two opposite effects. 12 divided by 2 makes the value smaller. But because I am now dividing by 2, I'm going to reverse, and instead of multiplying by 2, I'm going to divide by 2, and that makes the value bigger. I've got a big and a small. So 12 divided by 2 is 6. 2 divided by 2 is 1. 6 divided by 1 is 6. And notice that is the same as 12 divided by 2. So my multiplying and dividing, use multiplying and dividing, but you can't just always say, well, I've got a minus and a plus, so I should have, and in this case, I've got a times and a divide. No, it's not by operation, it is by effect. And this has to do with fractions, and I'm going to get into that on another slide. Because the top here, the beginning, is actually getting smaller, so dividing here is actually countering it and making it bigger. It's a little easier to see with fractions, but in the end, you know you've got to do it, because 12 divided by 2 is 6. And if I times by 2, I end up with 6 divided by 4, and I don't end up with 6. I'm changing the value. So two opposite effects. Let's look at some more examples. Okay, let's look at units. This may be a little easier before we get into fractions. Pretty straightforward and hopefully more relatable. 5 yards, and I need to change it to feet. Well, and pretend I don't know what my answer is yet. It's just the problem is how many feet in 5 yards. So I know I have to go from yards to feet. The unit is getting smaller. And feet are 3 times smaller than yards. So then my number has to get 3 times bigger. Unit gets smaller, number gets bigger. Similar down here, if I've got 8,000 meters and I need to know how many kilometers, if I go, and I know I'm doing this backwards, but it works both ways. That's why I'm doing this. Meters becomes 1,000 times bigger to become a kilometer. So 8,000 has to become 1,000 times smaller, so it becomes 8. And notice implicitly, 5 yards, 8 kilometers, this is multiplication. So you're going to use multiplying or dividing to figure out your answer. 2 days, how many hours in it? Days becomes 24 times smaller. Days divided by 24 becomes hours. 2 times 48 becomes my answer. Big, small, same amount. Well, I should say same proportion. I'm not adding or subtracting. I'm multiplying or dividing because the numbers and their units are connected by multiplication. Okay, let's hit fractions now. And we've got to remember its effect. I have a bigger effect that's in proportion to a smaller effect. Okay, so I've got 3/4 plus 1/3. We know we've got to get common denominators. We know the numbers on the bottom have to be the same. We're trying to get to 12 because that's the only way, combine only like things. So 4 has to times by 3. 3 has to times by 4. That part's obvious. Now, what do I do on the top? Oh, look there. Wait a minute. Shouldn't I, if I multiply, shouldn't I divide? And if I divide, shouldn't I multiply? Remember, it is by effect. 4 times 3 on the bottom cuts my pie into smaller pieces. Which would you rather have? A pie cut into 4 pieces or a 1/12 of a pie? A bigger number on the bottom, because of the dividing, actually it is making your fraction smaller. 3/4 is bigger than 3/12. 3/12 is smaller than 3/4. When I multiply by 3 on the bottom, I'm actually making my fraction 3 times smaller. So then, what do I do on the top to make my fraction 3 times bigger? Well, now it becomes clear. I've got to multiply. Dividing by 3 isn't going to make it 3 times bigger. Obviously, it's going to make it 3 times smaller because now I'm only going to have 1 piece instead of 3. So we knew the times 3 down here because I had to multiply by 3 to get my 12. That is like required. My question is, do I multiply or divide by 3 on the top? And I need to multiply because I was forced to make my fraction 3 times smaller. So now I've got to figure out, how do I make my fraction 3 times bigger on the top? Division won't work, only multiplying does. And so if you're going to make my pieces smaller, 1/12, then I want more pieces, 3 times 3, not less pieces. I want 9/12 of that pie if I can't have 3/4, which of course, they're the same thing, but okay. Let's clear out our mess. And now look at this. And of course, the thinking is going to be exactly the same. Why do I multiply by 4? Because I'm trying to get to 12. If I multiply by 4 on the bottom, a third now becomes a 12th, smaller. Oh, well, if my 1/3 just got reduced to 1/12, not good enough. I want more 12ths than just 1. So that's why I'm going to multiply by 4 on the top. Let's get some more 12ths in there. So I want 1, I want 2, I want 3, I want 4. There. Now I've got a third of a pie again. So smaller effect on the bottom, bigger effect on the top, and everything is happy. Do it on a calculator. 3 divided by 4 is 0.75. 9 divided by 12 is 0.75. I did not change the value of the fraction. 1 divided by 3 on a calculator is 0.3333. 4 divided by 12 on a calculator is 0.3333. I did not change the value of that fraction. Of course, now I just go ahead and combine only like things, and I've got 13/12. But the big small came into play up here. I made my fraction bigger on top in proportion to making it smaller on the bottom. All right, let's now look at scientific notation. A very common problem, especially in pre-algebra, especially in the science classes. So scientific notation says that you're going to have a digit, decimal, and then everything else to the right. Well, we start with an invisible decimal here. It's got to go 2 places smaller to over here. Well, my number, which is all one factor, because I'm multiplying here, and exponents is another shorthand for multiplying. So this is all one factor. So I'm going to do a bigger, smaller, all right here. So if I have made this part, this factor, 2 places smaller, how do I make my 10 to the 7th 2 places bigger? Well, 2 places, this is like dividing by 100, multiply by 100, my exponent increases by 2. So 2 places smaller is balanced out. It is countered by 2 powers bigger. 2.3 times 10 to the 9th. Okay, so now we can look at this fairly rapidly. If we remember, we have an invisible 1 power. My decimal has to move over here, and that makes it 1 place bigger. So my power will become 1 power smaller. 4 times 10 to the 0. We've got an invisible decimal there. Okay, so this got bigger, the power got smaller. Now we have 68. We're going to get 1 place smaller, so this has to get 1 place bigger. 6.8 times 10 to the 6th. Let's look at some polynomials now. And what we will notice is the parentheses. We have an outside 8 and we have an inside 2y plus 3. So if I want to make my outside smaller, I have to use multiplying or dividing because it is 8 times parentheses. So I make it smaller by dividing. 8 divided by 2 is 4. But I can't stop there. The outside got 2 times smaller, so the inside has to get 2 times bigger. And there are 2 terms in here, so they both have to get 2 times bigger. So again, it's the effect. Don't worry about, well, there's only one dividing, but there's 2 multiplying. That's right. It takes 2 little multiplyings because we have 2 little parts inside the big box. The big box is getting 2 times bigger, the whole inside, while the whole outside is getting 2 times smaller. Remember, it is the effect. So now let's do that. 2y times 2, 4y, 3 times 2, 6. So now what happens? We can check our work here. What happens if we do the full multiplying? I mean, why would you only want to divide by 2? Well, sometimes students only see, oh, hey, I can make it 2 times smaller or whatever else, and they only go part way. Oh, wait a minute. No, I really needed to get that down to 1. Okay, fine. Let's divide by 8 on the outside, so I'll multiply by 8 on the inside. So now I end up with 1, and of course I'll end up leaving that invisible in real life. But multiplying by 8 on the inside gives me 16y plus 24. Well, what happens over here? If I divide by 4, which will bring me down to 1. 4 times 4y, 16y. 4 times 6 is 24. Notice I get the same answer. I never changed the value of the problem. I changed the little mini values of the parts, but I never changed the overall value of the problem. Okay, so now a normal problem, we're going to take the 3, multiply it. So the 3 becomes 3 times smaller, and I get 1. So that means the inside has to get 3 times bigger. So 3 times x, 3x, 3 times negative 2, negative 6. As simple as that. That's what distributing works on, and we think, well, it's just multiplication, and it is, but it is a big, small action. That principle is never violated because it is keeping our beginning value and our ending value the same. So now if we have 4x plus 10 and we want to go the opposite way and we want to factor a 2 out of it, because I see 4 and 10 are both divisible by 2. So if I divide by 2 everything on the inside, and of course this will always have to be the same. I could have 5 terms in here. I will do the same thing to all 5 on the inside of the parentheses. And then on the outside I will come out and do the opposite. Since I'm dividing by 2 everything inside, I will multiply by 2 on the outside. And that's how I get my answer over here on the right. So 4 became twice as small, 2, 10 became twice as small, 5. The invisible 1 in parentheses became twice as big, and so that's how I factor. So 4x plus 10 gets pulled apart to an outside-inside, but put them back together, and you'll see it's the exact same thing. So you know you did not lose any value. Beginning, end, middle, everything in between, value stays the same. You're fine. You're good. You know you're correct. Okay, here's an example of fractions that you won't see until at least pre-algebra, maybe algebra, depends on the book. We don't like square roots on the bottom of a fraction. So a very simple trick is to simply square the square root. Multiply the root by itself. The root disappears. We end up with a whole number. Now notice square root 2 got bigger to a full whole number 2. So if the bottom of the fraction gets bigger, that is making the value of the fraction smaller. So what am I going to do to the top to make it bigger? Well, of course, I'm going to multiply, not divide, by the same amount, square root 2. So 5 times square root 2 is 5 square root 2, and of course we already have the 2, and we're done. So, this is just an example of fractions using square roots. And then what about reducing a root? Well, square root of 75 becomes an outside number and an inside number. We try to make the inside as small as possible. Well, how did we get here? What are the intermediate steps here? Well, 75 is the same as 25 times 3. Aha, now I see where we're going. Square root of 25 on the inside is the same as 5 on the outside. 25 is really not 25. It's being made smaller by the square root. And now 5 on the outside has no square root. It's the whole number. So we have another bigger, smaller. By pulling the 25 out and getting rid of the square root, I have a big, small going on at the same time. And this one's called reducing roots. So reducing roots down here on the bottom, rationalizing roots there on the top, big, small. Yet another example. And like I said, we will see many more because they come up in so many problems.